Should be recording. Anyway, as far as this quarter goes, we have just 3 units. And one of them, the first one is electricity, the second is magnetism, and the third one is special relativity. We'll have tests on electricity and magnetism, and then a comprehensive final that will include electricity, magnetism, and special relativity. And special relativity, it's roughly 1/5 of the quarter, but because you won't have been tested on it before, it might make up something like 1/4 of the final. So that's how that will work. I've put in a request to have a field trip to LIGO in kind of mid-May. I'm avoiding the last weekend in May because that's Memorial Day, and I'm asking to have it on a Friday. I don't know if they may be solidly booked by now, but I don't know that we'll be able to do that or not. Anyway, it'd be either May 10th or May 17th. And then what else do we have going on here? Oh, I avoid having it into June, although I used to like going in June, but it seems like most of the days in early June get taken up with graduation practice for those of you who are still in high school, and that kind of fouls things up. So anyway, we may have that field trip. I don't know if we'll be able to or not. Other things, that's about all I can think of for now. Anyway, we're starting with electricity, and we haven't been dealing with charged particles at all, although maybe we've talked about them sometimes. But first, we'll start with electric charge, and I'm guessing most of you know some of this stuff, that the charged particles with which we're going to be the most familiar are protons, and they have a charge of, I'm just going to write it as plus E, and lowercase e for a while is just going to stand for the fundamental unit of charge, and electrons have a charge of minus E. And once in a while, we'll mess around with other charged particles. We might talk about muons or something like this, but muons or pions maybe once in a while, but those have charges of just minus E2, E as well, I mean. And E for us is just going to stand for the absolute value of the charge on something. And the unit of charge that we'll be using is a Coulomb, 1.602 times 10 to the minus 19th, capital C, and C is the abbreviation for a Coulomb. It's one of those units that's named after a person, and so the abbreviation will get a capital C, and when you write it out as a word, it gets a lowercase c. So that's how that works. Now, in ordinary material, that's the fundamental unit of charge. It's either plus E or minus E, or if you've got a large object with a mixture of charge, it may add up to 0, but it'll be some multiple of this. And the value of this was found by Robert Millikan back in the early 1900s, kind of a neat experiment, Millikan's oil drop experiment. And it's one that I did as a
Natalie is struggling to get in the Zoom.
Oh, she is. Okay. I'll admit her. Okay. Joining. Yeah, one time I'd seen her on the list. Are you back in, Natalie? Looks like it. Yeah, now it just looks like 4. I'd clicked admit all and Natalie was on the waiting list then, but I need to fix that. So anyway, we should be good. Anyway, back in the early 1900s, Millikan determined the charge on the electron, and the Millikan oil drop experiment was one that is still done in senior physics labs. And by senior, I mean as an undergraduate senior, although I think I had friends who did it as a junior as well. However, that's something that determined the fundamental charge. Now, it turns out that quarks have weirder charge, but a proton, for instance, proton is made up of two up quarks and one down quark. And an up quark, a U, has a charge of, by the way, we use a lowercase q a lot of times to stand for charge of something. And an up quark has a charge of plus 2/3 E. That's kind of weird. And then a down quark has a charge of minus 1/3 the fundamental charge. So that's kind of weird. And a proton with the two up quarks would have 4/3 of an E from them, and then minus 1/3 from the down quark, and that adds up to 1 E. And then a neutron happens to have one up quark and two down quarks, and so that adds up to 0. So even though the neutron is always thought of as being a neutral particle, it's actually made up of 3 charged particles whose charge adds up to 0. We are not going to study these things at all this quarter, so don't worry about these. I think I've got a dying pen. Anyway, that's something that happens. Early in this unit, we're going to, well, throughout things, we're going to be considering things which are conductors that can conduct electricity. And a conductor is something that has free charges, basically free electrons, and electrons that can freely move, and they move in response to an electric field. So an electric field or an electric force. We're going to start by talking about electric force today, and then tomorrow we're going to be starting to consider electric fields, and that's an additional level of complexity that we didn't have fall quarter, but it's actually, we did deal with something like that, and it was the gravitational field, which is actually lowercase g, is the acceleration due to gravity. And you can think of that as being the force per unit mass. Do we have anybody else? Yes, we've got James over there in the waiting room. I better keep an eye on that. The waiting room, I've got that sort of off to the side. Anyway, we dealt with something like electric field fall quarter, except it was gravitational field, and it was where we thought of the force on something as being its mass times g. Well, this quarter we're going to be doing something like it, except the electric force on something will be that object's charge times the electric field. And the electric field is sort of like the acceleration due to gravity. This is a force per unit charge. This is actually a force per unit mass. So we'll be dealing with things like that. Okay, but a conductor is something that has electrons that can freely move. You could think of it more generally in terms of charged particles that can freely move, but for the matter we're familiar with, it's the electrons that are doing the moving. The protons are kind of stuck in place along with their atoms. we'll have insulators, and insulators are things that do not have electrons that can freely move. So you can have an electric force acting on an insulator and things don't move around in there. Although if you make the electric field strong enough, you can still do that. But let's go on and try some example problems here. And we'll start with something that maybe you've heard about, the Bohr model of the atom. And this was an early model of the atom in the early 2000s or early 1900s, excuse me. And up until that time, people had just started investigating the atom for a long time. Well, a couple of decades at that point. They knew that atoms had negative charges in them called electrons that had just been discovered in about 1897. And then they also knew that atoms, for the most part, were neutral, or most of the time they were neutral. So they had negative things in them, but they didn't know what else was in them, except that it must be positively charged, because most of the time they were neutral and their charges added up to zero. So people started investigating that. One of the early models was something called the plum pudding model, and they imagined that there was some stuff that the electrons were embedded in, and it was positively charged, and they had no idea how they were acting in there. And then in, let's see, I think about 1908, Ernest Rutherford did an experiment where he was trying to learn something about the distribution of that positive charge in the atom, and discovered that all of the positive charge in the atom was concentrated in a tiny nucleus. And after that, they started learning eventually what the nucleus was made of. And this is stuff that you probably know. But in the Bohr model, which was shortly after Rutherford discovered the nucleus, the electron and proton are treated as small particles, point particles. Actually, when Bohr did this, he didn't know that there were protons in the nucleus. All they knew was that the nucleus was positively charged, and it was really tiny. So anyway, but he had this value for the distance between the electron and the proton, at least in one of the states of an atom, of the hydrogen atom. And each has a charge of magnitude 1.60. If you add another sig figs, it's 1.604 times 10 to the minus 19th coulombs. And calculate the attractive force acting on the electron at this distance from the proton. Well, this is your first introduction to something called Coulomb's law. And Coulomb, way back in the, might have been late 1700s. I'd have to look up just when he did that. This is Coulomb's law. And your book writes this constant that shows up here with a little subscript, K sub E, and it's going to look like the gravitational force law. It's Q1, Q2 over R squared. So the gravitational force law had a constant. This has a constant. It has the property of one of the objects, the property of another object, and it's divided by the distance between them squared. And that's Coulomb's law. So, and he's the guy that the fundamental unit of charge is named after. And this is just asking us to do a calculation with that. Well, K sub E is actually made up of more fundamental particles. It's equal to 1 over 4 pi, and then something called epsilon naught, which is a much more fundamental unit of matter. And let's see. When I took this class, we didn't write it as K sub E. We always wrote it as 1 over 4 pi epsilon naught. There are places where you actually pull that epsilon naught out and deal with it by itself. Oh, epsilon is a Greek letter, and that's my approximation of it, by the way. Anyway, it's equal to about 8.99 times 10 to the ninth, and its units are, well, this is going to be Coulomb times Coulomb squared. This is going to be meters squared, but we somehow have to end up with newtons. And so the units of this end up being Newton meter squared per Coulomb squared. You may remember the gravitational force constant was Newton meter squared per kilogram squared. So it's just a proportionality constant, and it's got that value here if you're using the metric system. I don't know that there's a version of this for the American system of units or not. Thankfully, that isn't something that anybody ever has to learn, if there even is one. But there was an earlier system of units called the CGS system. It was centimeters, grams, and seconds. There was a different unit of force in there called a dyne, a unit of energy called an erg, and the unit of energy is actually still used in astronomy in some fields. So that was an old unit, but we won't have to deal with that. We're just going to use this one. So we just have to plug in the values here and calculate this force. And it would be 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. And then each of these things has a charge of plus E. And if all we're after is the magnitude of that, this could be the charge of the proton, this could be the charge of the electron. If we're just after the magnitude, we can just take E squared. And so that would be 1.60 times 10 to the minus 19th coulombs, and we square that, and then divide by the Bohr radius of 5.29 times 10 to the minus 11th meters. And in the Bohr model, and that's squared. How about 2.9 instead of 9.2? Don't talk and write at the same time. Anyway, Bohr assumed that the electron was orbiting the nucleus of the atom, and in the hydrogen atom, that was the distance when the hydrogen atom was in its ground state, its lowest energy state. That's what it was. So this is the number that's supposed to be down there. All right, well, how big is that force here? Man, I haven't used a calculator in a while. Okay, and so for the force, I get something that looks pretty small, 8.22 times 10 to the minus 8th newtons. But remember what this force is acting on, an electron, which is a dinky little thing. And then, just for fun, we calculate the gravitational attraction between the electron and the proton, and the mass of the electron is that, and the mass of the proton is that. So let's just plug in the numbers and see how big the gravitational attraction is between those things. And it would be G times the mass of the electron times the mass of the proton divided by the same radius squared. Sometimes that Bohr radius gets a little subscript of a B on it. I don't know if it's going to matter much. We probably won't use it much after this, but remember capital G was 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. and then mass of the electron, 9.11 times 10 to the minus 31st kilograms. That of the proton, 1.67 times 10 to the minus 27th kilograms. And then that distance again, 5.29 times 10 to the minus 11th meters squared, and kilograms times kilograms squared, that'll divide out with those. Meters squared up here, meters squared down there. So we end up with newtons again. And let's see what it is. Actually, just looking at it, you've got a 10 to the plus 9th here. You've got a 10 to the minus 19th here that's squared, giving it 10 to the minus 38th. And that's the numerator. But here you've got a 10 to the minus 11th in the constant, and then the mass of the electron is a minus 31 instead of a minus 19, and the mass of the proton is a minus 27. So it's going to be a lot smaller for the gravitational force. Okay. I don't think I've used a calculator in a week and a half or so, or maybe a week. I don't know. Anyway, I get about 3.63. Is that right? Maybe. Times 10 to the minus 47th newtons. And if I divide this by that, yeah, I think that's about right. Minus 22. That's minus 11, so that'd be 10 to the 11th. 10 to the minus 32. I hope I didn't punch something in wrong. I better check that real quick. Yeah, I'm pretty sure I got all these punched in right. Minus 27, minus 31. Oh, that's right. Tiny. Anyway, but if I divide this one by that one, so 8.22 minus 8. I get about that. This one is about 2.3 times 10 to the 39th bigger than that one. And that's huge. The gravitational force is by far the weakest force in nature. And the electric force is the second strongest force in nature. It's weaker than the strong nuclear force, but only by a factor of about 100 when both of them are acting together. So that's something that happens. So anyway, there's our introduction to a Coulomb's law problem. Okay, then calculate the acceleration of the electron due to the force we calculated in part A. Well, let's go back and see what that force was. 8.22 times 10 to the minus 8 newtons. So and the acceleration of the electron is going to be that force divided by its mass. So 8.22 times 10 to the minus 8 newtons, and I'm dividing by the mass of the electron. Pretty tiny. but that's still, you can see it's going to be a big positive value with a 10 to the minus 8th on top and a 10 to the minus 31 on the bottom. And let's see. Oops. Okay, I get something in the neighborhood of 9.02, not that we need that much precision here, but times 10 to the 22nd meters per second squared. When you divide a Newton by a kilogram, you get meters per second squared. So that's a pretty big acceleration. Now, assuming the electron is traveling in a circular orbit and the acceleration is entirely centripetal, calculate the speed of the electron. Well, the centripetal acceleration, if that's what it is v squared over r. Man, a lot of stuff from fall quarter showing up again. And so v squared is going to equal r times a, and v will equal the square root of, let's see, r was 5.2, whoops, 29 times 10 to the minus 11th meters times that acceleration, 9.02 times 10 to the 22nd meters per second squared. Looking at the units, meters times meters per second squared is going to be meters squared per second squared. And when you take the square root, you get meters per second. So and I get around 2.1, yeah, maybe 2.19, something like that. Anyway, times 10 to the 6th meters per second. And that's a pretty good clip. That's 2/3 of a percent of the speed of light. Okay, as the acceleration's whizzing around in there. This was a problem for the Bohr model that in the 1800s, people had determined that when you accelerate a charge, either speed it up, slow it down, or make it change direction, it will radiate energy or require energy, possibly, but this is a tremendous acceleration. And so those electrons whirring around the nucleus of the atom should have been radiating their energy, which means they'd spiral into the nucleus and get absorbed by it somehow. And all atoms should have ceased to exist almost instantaneously. And Bohr got around that by saying electrons orbiting the nucleus of an atom don't radiate energy. He didn't say why, he just said they don't. And later the Bohr model was replaced with the quantum mechanical model, which Bohr had a lot to developing, or a lot involved with developing that. And so this wasn't the final model for Bohr, but it's still the picture of the atom that most people carry around in their head, if they have one at all, that there's a positive nucleus, and then they imagine these little electrons whizzing around there. And so you see a symbol that kind of looks like that. And that's supposed to be the atom. And we now know that electrons do not orbit the atom, although we still use terms like orbitals when we're talking about their energy levels. But they behave much weirder than that. And maybe later in the quarter, we might talk about some of that. Okay. Let's do another one. And this is going to bring us back to some of the stuff we did fall quarter. We're going to be expressing things with I hat, J hat notation, which is probably just about invisible for you there. I don't have this file posted up online for you yet. Some of my equations look pretty weird on here because this was from, oh man, I'm not sure when I typed this, but it was back when I was using equation editors that haven't translated well. And it's working better now that I'm using LaTeX in Open Office or Office Libre. Anyway, but we've got 3 protons here, P1, P2, and P3. And we'd like to calculate the net force on P3 due to P1 and P2 and express that force in I hat, J hat notation. Well, the easiest thing to do is to calculate the one on P3 due to P2, and that'll be a force that's going to be in the downward direction, in the minus J hat direction. And I could call this F32. It's the force on 3 due to proton 2. And then there'll be another one here that's going to be down in this direction. And that'll be the force on 3 due to electron 1 or proton 1. Excuse me. And it's going to be kind of different to deal with this thing. By the way, the units on the axes here are nanometers, and so those are what we have. So we ought to be able to figure these things out kind of. First thing I can do, though, fairly easily is to calculate the magnitudes of each of those forces. F32 will equal the K sub E, that 8.99 times 10 to the 9th. And then each of these has a charge of E. They're protons, and protons all have a charge of plus E. So these are going to be repulsive things. Actually, just unconsciously, I drew these things being in the correct direction because they are, the proton here will be repulsed by this proton and by that proton. So we can say that, but we'll just have K sub E times E squared times, I can call it R32 squared, the distance between these two things. And it looks to me like the distance between them is 3.00 nanometers. So I just have to square that. So the magnitude of this force, 8.99 times 10 to the 9th. And I'm going to run out of room as usual. Oh, well. Newton meters squared per Coulomb squared. And then times the charge, 1.60 times 10 to the minus 19th coulombs squared. And I'll divide by the distance between them, the 3.00 times 10 to the minus 9th meters. And that gets squared. So the magnitude of F32 is going to equal whatever that works out to. Oops. Somewhere here, I forgot to put a, oh, I see. I put a divided by between those two, and I ended up with an absolutely insane value for this force. So I need to replace it with a times, and it should be good now. I get about 2.56 times 10 to the minus 11th newtons. Let's see if that makes sense. 10 to the minus 38 that'd be 10 to the minus 29th. 10 to the minus 8. 10 to the minus, yeah. Magnitude wise, that's fine. Okay, now if I write that as a vector, it's just going to be, put an arrow on top, and it points in the minus j hat direction. So it's minus 2.56 times 10 to the minus 11th newtons in the j hat direction. So that wasn't so bad. Okay, let's figure out F31, the magnitude of it first. And this one's going to be a little bit trickier to try to figure out. Actually, first thing I'll do is figure out this angle here. Theta is going to be the inverse tangent of, let's see, 3/4. The opposite divided by that. 3.00 nanometers divided by 4.00 nanometers. That's just opposite over adjacent, and I just imagine making a right triangle here. And so the magnitude of theta is going to be not too bad. Oh, I better make sure what I'm in. I'm in radians, so I have to get out of there. Not that it would matter, I guess. Okay, 36.9 degrees is the value of that. Okay, so the magnitude of F31. Numerator is going to be the same. It'll be 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times, they each have the same charge, 1.60 times 10 to the minus 19th coulombs. That gets squared, and they are separated by, I've got a little right triangle here, but the right triangle distance is squared, the hypotenuse of it. It would be 3.00 times 10 to the minus 9th meters squared plus 4.0. I can do this in my head. I could have done that. It's a 3, 4, 5 right triangle. Oh, my phone's going to be ringing for a little bit here. Yeah, anyway, that'll be combined to give me 5.00 times 10 to the minus 9th meters, and I can square that. So I can quickly calculate this thing. Had some weird little thing pop up, but okay, and I get something a little bit less than that one. It's 9.21 times 10 to the minus 12th newtons. And if I figure that out in this kind of notation here, I think of this thing as being F31 as a vector there, and this is 36.9 degrees. So the x component is going to be F31 times the cosine of that angle, and the y component is going to be F31 times the sine of that angle. So F31 as a vector will equal. I would get 7.36 times 10 to the minus 12th newtons in the I hat direction minus oh, where was I? There I am. I get minus 5.53 times 10 to the minus 12th newtons in the j hat direction. And the sum of those two, F32 plus F31, I've only got one of them with an I hat component, so it'll be 7.36 times 10 to the minus 12th newtons in the I hat direction, minus, I have to add these two things together to get the j hat component. Let's see, this is actually 0.55. Add it to that. Yeah, I better do that in my calculator. I don't trust my head this morning. I would get minus 3.11 times 10 to the minus 11th newtons in the j hat direction. And I hope I did that right. All I did was add this thing to that thing up there. So in I hat, j hat notation, that's the value of the force. Now, the direction and magnitude of that force, here's what I expect. When I add this force to this force, I'm going to get, imagine the parallelogram rule, I'll end up with some big force down here in this direction that's going to be partway between these two. And so the angle that it makes with the positive x-axis is going to be bigger than 36.9 degrees, maybe partway between there and 90 degrees, I guess. But we can see how that's going to work out. The magnitude of this net force, if I call this F net with an arrow, it'll just be the sum of the squares of those things. I'll get about the magnitude of it 3.3 sig figs. It's 20 times 10 to the minus 11th newtons. And that angle, which I think I'll call phi, that it makes with the thing will be the inverse tangent. And this is going to be measured clockwise from the positive x-axis. Inverse tangent of its y component divided by its x component. So I'd have 3.11 times 10 to the minus 11th newtons divided by the x component, 7.36 times 10 to the minus 12th newtons, and the newtons go away. I didn't even need to write them down. But Yeah, it is an angle between 37 and 90. It's 76.7 degrees. So the magnitude of the force is 3.20 times 10 to the minus 11th newtons. And the angle it makes with the positive x-axis is measured clockwise from the positive x-axis. It would be 76.7 degrees. So all of this stuff is using Coulomb's law here and getting a little bit of practice again with I hat, J hat notation, which we haven't used for a while. Okay, one last problem. This is going to introduce something, and I'm not sure how far I'll get on this. I've got a video I recorded, let's see, 2 years ago with the previous, or the person who left in June, Jim Lynn. He was teaching it, but his wife had just had a baby for the first 2 quarters of spring quarter 2022, I was teaching some of this, and I hung on to some of the videos that I did during that stretch. And if I don't finish this today, I'll provide a link to that video so you can see it. But anyway, we have an insulator in the shape of a thin cylinder that has a uniform distribution of charge placed on it. So it's an insulator, which means charge is not free to move around on it. So when you put charge on an insulator, it just kind of stays put wherever it happens to be. If you did the same thing with a conductor and you brought some charged object near it, the negative charges in a conductor would move away from that electron, leaving behind positive atoms. And anyway, but here we've just got a uniform charge density. And it's got 6.0 times 10 to the minus 15th coulombs per centimeter on it. I'm probably going to have to change that to coulombs per meter, maybe, but we'll see how that works. But determine the force on a free electron 5.00 centimeters from the end of the cylinder in line with it. So here's an electron, and then determine the acceleration of the electron. Well, let's see. It looks like this charge that's on this thing is positive, so it's positively charged. Now, when it says charge is placed on it of that much, the way that you would actually do this is to remove electrons from this thing, because it's not like you can add protons to something like this. Those are the positive charge carriers in ordinary matter, but you can remove electrons. So if you bring a positively charged object near this thing, you can steal electrons off of this. And when you take electrons away from something that was originally neutral, you leave behind an imbalance of charge, and it's positively charged. Kind of weird things to be thinking about that. Try to read parts of chapter 21, I think, is what we're looking at here, and start getting familiar with some of these ideas, because it's good to have a bit of a conceptual background on this stuff. Anyway, we want to know the force on a free electron in line with it, and then determine the acceleration of the electron. Well, once we get the force, acceleration is just going to be somewhere down here in the bottom corner. It'll just be F over m, so we'll divide by the mass of the electron. The hard part, though, is going to be doing this. Now, here's why it's hard. We know what Coulomb's law looks like. It's K Q1 Q2 over R squared. But this cylinder here is a whole bunch of different distances away from the electron that's sitting here. And so somehow we're going to have to learn to deal with that. So we're actually going to have to integrate here. Now, I'm going to let x equals 0 right here at the left end of the rod. And here we have x is equal to 15.00 times 10 to the minus 2 meters. The electron is out here at x equals 15 and 5 is 20, 20.00 times 10 to the minus 2 meters. That's the position of the electron. Well, I need to somehow set up an integral. So what I'm going to do is imagine a little tiny slice of this cylinder that has a length of dx. And I'm told this is the charge density that's placed on this uniform cylinder here, this thin cylinder. Okay. Let's see. We'll have occasion in this class to use charges per unit area. We'll have occasion to use charge per unit volume, and we'll have occasion to use charge per unit length, which is what we've got here. And we'll use different letters for them. I think generally when we're doing charge per unit length, we use lambda to stand for that. And in this case, it'll be plus 6.0 times 10 to the minus 15th. Interesting, we only have 2 sig figs on that, but that'll be coulombs per centimeter. But if I multiply that by 10 squared centimeters per 1 meter, I'll get 6.0 times 10 to the minus 13th. Coulombs per meter. And that's what lambda is going to be. Well, how much force is going to be on that electron out here due to a little bit of little chunk of charge there at dx? And I'm going to let dx here be a distance x away from the origin. And I'm going to I'll just let that be x sub e, I guess, and see how this is going to work. Oh, this is positive, that's negative. And I'll call it df. This is going to be the little bit of force that's acting on the electron here due to a little bit of charge there. This is something maybe you haven't done before. I'm sure you haven't done this, but maybe in a math class they did something, in a calculus class you might have done something where you added up a contribution from one thing to figure out the effect somewhere else. I don't know, but maybe this is completely new. Anyway, df is going to equal, in magnitude, it'll be k sub e times the amount of charge on this thing. Well, the amount of charge, since this is charge per unit length, and this has a length of dx, it'll be lambda dx. So k sub e times lambda dx, that's the charge on this little tiny chunk here. This is the charge on the electron over here, so that's just going to be E. And then I'm going to divide by the distance between this little chunk and this thing here, which is, what is that? That distance squared. Well, this is x sub e. It's a constant value. It's going to be x sub e minus x. So, and that distance has to be squared. And as long as we're really careful about writing everything in meters, it ought to work out okay. Now, that's the charge on this. It's going to be to the left because this is positively charged, this is negatively charged, and the electron will be attracted in that direction by the positive charge. And here's the tricky expression. This is going to become my integrand. to find out the total force, I would have to integrate over this entire cylinder here. But the hard part was getting to here. Okay, this is actually Coulomb's law. It's K sub E. Q1 is lambda dx. Q2 is the electron that's out here. And then I divide by the distance between them squared. And that's a tricky calculation, but let's see where we go with it. Well, to get the total force, I have to integrate the dF, and what I have to integrate is this thing. K sub E lambda dx times E divided by x sub E minus x squared. Okay, well, I'm almost have something I could integrate. What are my limits of integration? Well, I'm going to integrate from the left end of this thing, where x is 0, to the right end, where x is 15 times 10 to the minus 2 meters, and I'm going to call that x sub L, I think, so I don't have to write it again. Okay, so I go from 0 to x sub L. Okay, well, what work do I have to do? Well, turns out I can simplify this a lot. K sub E is a constant, lambda is a constant, E is a constant. I can pull those out of the integral, and I'll have K sub E times lambda times E, and then times the integral from 0 to x sub L, where x sub L is just 15.00 times 10 to the minus 2 meters. And the integrand left behind is dx divided by x sub E minus x squared. Okay, I'm about the world's rustiest integrator. But what I do for something like this is just do a change of variables. I'd let u equal x sub E minus x. So that's one thing I'll do. And I don't want to run out of space, so I'm going to let u equal x sub E minus x. Du will equal, well, when I take differentials of these things, that's a constant. So it's gone. It'll be minus dx. And when x is equal to 0, u will equal x sub E. So that becomes the lower limit there. When x is equal to x sub L, let's see. I better write these down. And when x is equal to x sub L, u will equal x sub E minus x sub L. And so this integral will become K sub E lambda times E. All of that stuff's outside the integral. My new limits are going to be x sub E to x sub E minus x sub L. And inside here, I'm going to have minus du. If du equals minus dx, then dx is minus du. So, and then here, I'm just going to have u squared. Okay, well, I've got a minus sign here. If I swap the order of the limits, I can have a plus sign there. And then I would have the magnitude of that force is going to equal K sub E lambda E times the integral from x sub E minus x sub L to x sub E of just du over u squared. Okay, that's the, you could probably just look up that integral in well, online, nobody uses books for it anymore, but when I took it, that's what I would do. But the integral of du over u squared ends up being minus 1 over u, I think. So if we do that, I'd get k sub e lambda e, and then minus 1 over u evaluated at x sub e minus x sub L and x sub E, and I end up swapping things order-wise again and evaluating that k sub E lambda E, and I'd be multiplying by 1 over x sub E minus x sub L minus 1 over x sub E. And at this point, I think we could probably punch numbers into that because whatever it ends up being anyway. So k sub e, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And then I multiply that by lambda, which is 6.0 times 10 to the minus 13th. Coulombs per meter times E, which is 1.60 times 10 to the minus 19th coulombs. And by the way, everything I've done here, I'm just after the magnitude of this force, okay? At the end, I have to come back and remember, oh, okay, the force is going to be in this direction because it's acting on an electron. I could have put a minus sign in here for the charge on the electron, but I'm comfortable with just keeping track of things and remembering to go back and knowing that it'll be pulled to the left. Okay, and then I'll have 1 over x sub e minus x sub L is going to be 5.00 times 10 to the minus 2 meters minus, oh, I still ran out of room, 1 over 20 times 10 to the minus 2 meters. Then I can figure out what the size of that force happens to be. This took a while. Although I haven't lost anybody yet, as far as I know. My stomach's growling. I need to eat lunch soon. Syntax error. Oh, great. Somewhere in the thing I just typed in, I had a. It should be that kind of minus. I think I had one too many parentheses. Okay, I think that force is 1.30 times 10 to the minus 20th coulombs. But I'm not sure. Actually, one reason it's so much smaller is because this distance is in centimeters, and before we've been talking about nanometers and things really tiny. So that's probably what the magnitude of the force happens to be. Okay, I'm not going to worry about the rest of it, but the hard part was getting this thing set up and then picking the correct limits for this calculation. And we'll have some more practice with doing things like that. But for today, that's enough. I'm going to post this video as soon as I can get it processed. And then I'll also have a homework 1 up for you today, so you can start working on that. Otherwise, I'll see you tomorrow. And for labs this quarter, I think we're going to be doing some electronics labs. So tomorrow will be a brief introduction, not so brief actually. It'll take time, but we'll be looking at using electronic instruments to measure resistance tomorrow, actually. So I'll stop there. Stop the recording.